Hey everybody, my name is Taylor Sparks. I'm the editor-in-chief at Integrating Materials and Manufacturing Innovation, and I've got a new paper for us to read. It's Hybrid Algorithm for Filling in Missing Data in EBSD Maps. Now, maybe you've never heard of EBSD maps, but they're sort of like the love child between electron microscopy and X-ray diffraction. Whereas electron diffraction can give you an image of the microstructure, which is very valuable. X-ray diffraction gives us phase information, which is also very valuable. EBSD can do both. You can see in this image here, you can see here's what the micrograph looks like, and now you have colored regions representing the orientation of different grains, including which phase they are. So this is a really powerful tool for telling you if there's texturing present, how different phases are distributed, what grain boundaries look like. It's a really great tool, but you can have missing data. And lead author Emmanuel Atindama at Clarkson University and co-authors, including corresponding author Prashant Athavale at NIST, have developed a tool for filling in some of that missing information. They first off point out that EBSD maps are imperfect. They are very prone to being noisy, or they can have an incomplete appearance, and this compromises our ability to get information out of them. They talk about that there are recent advances in image in painting. The whole field of deep learning has done a lot of this, using generative image synthesis, particularly those using deep learning approaches, GANs, diffusion, Fourier convolutional networks. But they point out that these methods rely on, first off, they focus on generating realistic looking images, and they require a lot of training data and compute time. And what they'd like to achieve is similar results with modest amounts of data and compute time. And specifically, they point out that there's also some key differences in EBSD and real images. For one thing, they point out that in a traditional image, the pixel value is the intensity, but here we have different information encoded in the image, and so the comparison is not apt. For example, they say, unlike natural images, the pixel value, where it represents an intensity in a natural image, in EBSD maps, we now encode that value with the orientation data using the Euler angle. And therefore, the metric that you use for similarity in the reconstructed image is just not going to be the same. They become ineffective for EBSD. We need something else. We need a different loss function. They also point out that there are exemplar-based algorithms, but these sometimes fail to produce sort of reasonable grain boundaries in the EBSD. One of those is this paper, by the way. One of the papers that they built on is this Cremonesi paper from 2004, which is a region filling and object removal using exemplar-based image in painting. They took some inspiration from this. They go beyond it, though. They outline a novel hybrid approach, right? They basically say here, they say, in the proposed approach, we're first going to obtain an approximation of the in-painting using a machine learning approach, and then they're going to use that approximation to find the best exemplar method for the EBSD map. And the result is that it works really well. Here's an example. On the left, you see a clean, EBSD map. In the middle, it's a noisy EBSD map. And on the right, now you see a missing region used for demonstration. Okay, and these were generated using Dream 3D. Now down here, you can see what happens when you try and infill it with different approaches. The one on the far left is just using the original Cremonesi algorithm. In the middle, now you have the results using a sum squares of disorientation. And on the far right, now you have a different dissimilarity metric. It is your sum squares of disorientations of dissimilarity, but measured with Euclidean distance penalty. So it's their novel approach that they're using here. And the results speak for themselves. And you see in this table here, comparing the reconstruction error when you knew what it should have been and you compare what it actually produces, how dissimilar is it? You have large variation with Cremonesi, lower variation, and the lowest variation with their modified approach, with this hybrid approach. Something that I appreciate is that they tested this not just on Dream 3D simulated microstructures, but on real data, right? So this is real EBSD data collected at NIST, and you can see the result of the in painting, right? Here's the original real EBSD data, and you can see that it's got some missing segments to it. And then in the middle, they used a nearest neighbor in painting, and then here they used their proposed in painting, and the results just are really pretty great. So I hope you'll take a look. I think we're going to see more and more automated analysis and extraction of information from large data sets as we increase our throughput of manufacturing materials and characterizing them. And infilling data, I think, is going to be an important part of that.